that do not necessarily commute, we have to think a little bit about what this expression really means. And so the way we define this is that that's what we always do in quantum field theory. So what you do is you just draw two little dots here, and you already feel much better. So that means you normal order it. And what does normal ordering here mean? Well, normal ordering here means that AL, AM is equal to, well, it's either equal to AL, AM, or AM, AL. And we said that the positive modes are the annihilators and the negative modes are the creators. So the annihilators should stand to the right of the creators. So we take this to be that if m is bigger than 0 and that if m is less than 0. I mean, there are different ways in which you can do it. It doesn't really matter. You see, the only term where this ever matters is if one is positive and one is negative, and they have exactly the opposite sign, so that'll be good enough. So that's one way of defining the normal ordering. And then this is a specific operator that is well defined, and it's well defined on the Fock space. So this then Ln is well defined on the Fock space. Remember, the Fock space is created by having finitely many A minus N1 up to A minus NL acting on some ground state. And this state will be annihilated by the positive AMs. So once you've done that, then this expression will make sense because most of these terms will simply vanish. The sum on any such Fock space term, there will be only finitely many terms contributing from this infinite sum, and then you can just recursively calculate it by applying commutation relations to your heart's delight. Okay, so now the LNs sound like this conformal transformation generator, so we should see whether they have anything to do with it. So what should this mean in this current context? Well, what we would want to calculate is the commutator of Lm with phi left of z. And now you see phi left of z is a specific mode expansion in terms of these modes. And Lm is a specific expansion, so that's something we can now calculate. So let's just calculate what we find. Well, before we attack that, let's do a slightly simpler calculation. You see, let's work out what it does on the individual ANs. So let's work out what the commutator of Lm with an AN is. Okay, we'll just write down the formula. So that's the formula over L. Obviously now the dummy variable I shouldn't call n because this is a fixed n and here I'm summing over L. So let's call the dummy variable L. And then I have to take the commutator of AM minus L, AL, with AN. Now, contrary to what I just said, for this calculation, actually the normal ordering doesn't play any role whatsoever because whichever order it is, you're going to get two terms and they're either going to stand to the left of each other or to the right of each other. But once you've calculated a commutator, the answer is a number and you don't care whether it stands to the left or to the right of it. So for this computation, it's actually totally irrelevant whether I write these dots or not. In general, it plays a role, but for this computation, it doesn't. So what am I going to get? Well, so you have a product of two things with the third, and as you commute this through, the third guy has to get past the second guy, and then he has to get past the first guy, so there are two terms. So there's a sum over L, and there's one term which is AM minus L, commutator of AL and AN, and then there's a second term, commutator of AM minus L with AN times AL. And as I said, it doesn't really matter in which order I write them because this is a number and it'll be a number on the left and a number on the right. It doesn't matter. And this term, you see, is equal to, according to this calculation, equal to that. So this will be equal to, it'll be convenient. You see, you can either write this as m times delta m minus n, or you can write it as minus n times delta mn, because m is actually equal to minus n. So I'll write this as minus n times, and then this will be delta L comma minus n, and this I write as minus n times delta m minus L comma minus n. Or another way of writing this is simply to say L plus N must be equal to 0, or M minus L plus N must be equal to 0. Okay, so I'm going to get a factor of minus N from here, a factor of minus N from here, and then L has to be equal to minus N, so this becomes AM plus N, and then here L has to be equal to M plus N, so in both cases this just becomes minus N times A d M plus N mode, right? This is just, I mean, L always becomes the sum, or the mode number just becomes the cell, and this coefficient is minus N in both cases, and then I have a half here, so a minus, it gives me a minus N altogether. So this is the commutation relation of Lm with An. Okay? And obviously the other term I have to calculate is, I mean, I'm interested in taking the commutator of this with this. So now I know what it does here. Okay, so I have to, so with A0, it'll be 0, because if n is 0, then it's 0. But I have to calculate the commutator with Q. So what I have to calculate is Lm with Q. And this works similarly, except now obviously only the only generator that doesn't commute with Q is A0. So that the terms that will contribute will be the commutator of, so there will be an AM A0Q term. Somehow this thing is not. So I'll have this term, and then the other term will be A0, comma Q AM, right? Again, by the same token. And then A0, comma Q is minus I over 2. So this becomes an I over square root of I over 2 times, well, this 2 goes away. So this I, and this becomes a minus I. So this becomes 1 over square root of 2. And then the 2 cancels the fact that I have 2 terms. And then what I'm going to get is simply AM. Okay, so now I've calculated what the commutator of Lm with all the ingredients in phi left are. And now I can calculate what the commutator of Lm with phi left is. Well, the first term apparently just gives me 1 over, and now I've probably goofed in some form, square root of 2 times AM. At least that's what I would have liked. So you mean I have this is a half, so then there's an I here, something like that. Yeah, but I think I've gone wrong. Somehow I think this should have a factor of square root of 2 the other way around. Because then I'll be much happier. So let me make let me be happy. I think I'll be much happier this way. I think you'll also be happier. So let's make all of us happy. And then, so if this is the case, then if I take the commutator with Q, then the half with the square root of 2 turns this into a 1 over square root of 2. And then I'll have to hope for the best. So it probably gives me an I over square root of 2. Actually, I could just check what it says here. That is a smart way of solving this problem. It says actually minus I over square root of 2. Oh, there's probably some convention that's gone wrong. Anyway, so don't nail me down on this one. So this is what comes from here. From here, you're not getting anything, and then you're going to get plus I over square root of 2 times 1 over n. So here we have a sum of n not equal to 0, and the commutator of Lm with an gives you minus n over am plus n. So this cancels the 1 over n, and then it turns this into a minus sign. So probably I also want to have a minus sign here. And then I have an am plus n times z to the minus n. So the upshot of this should be that this is equal to minus I over square root of 2, the sum over all n, a m plus n, z to the minus n, where the term with n equal to 0 is simply that term. And now we want to write this, we want to rewrite this in terms of the modes am. So we introduce Newton mode numbers n hat being equal to m plus n. So then n minus n is equal to m minus n hat. And then this looks like minus I over square root of 2, the sum over all n, a n hat, z to the m minus n hat. And therefore, this looks exactly like, and now I have to check again. So if I've done things correctly, this should be z to the m plus 1 times d by dz on phi left. Right? Because if you take the phi left derivative, you get a minus n minus 1. So you want to write this as m plus 1 minus 1. So you want to write this as m plus 1 minus n hat minus 1. So the factor of z to the m plus 1 is in addition to what you would have had for the mode expansion of d phi. So what you learn is that the commutator of Lm with phi L is just z to the m plus 1 d by dz of phi. So therefore, remember, that's exactly how the local conformal transformation acts. So we see that this operator is implementing the conformal transformations on the fields. So it's sort of what this notation suggested, and in fact, that's what this calculation demonstrates. Okay, so now that we know that, we know already a lot about the commutation relations of Lm with Ln, because you see, we can use the Jacobi identity. So we know that any commutator will satisfy the following identity. If I first apply Lm and Ln to phi L, and I subtract from it Ln, Lm phi L, I know this must be equal to Lm, Ln phi L. This is just the Jacobi identity, right? I mean, you know that if you have commutators, then you always have the cyclic product of commutator AB with C plus BC with A plus CA with B is equal to 0. And if you rejig this, you see that this is exactly of the form of a Jacobi identity. Because you see, if you invert the order there, then you get a plus sign here, then this is one of the other terms here. And this term, if you bring it to the other side and you get a minus sign, but you turn around the order of the big bracket, then it's the third term missing. So this is simply a consequence of the Jacobi identity. So given that we know what Ln does on this and Lm does on this, we can work out what the commutator of Lm with Ln will do on it. So let's just work it out. So what is this? Well, Ln on this acts like z to the n plus 1 d by dz. And now we have to be a little bit careful here, so because this is just a differential operator, whereas this is an operator in the space of operators acting on this Fock space. This differential operator goes outside, so this becomes z to the n plus 1 d by dz times the commutator of Lm with phi, and the commutator of Lm with phi is z to the m plus 1 d by dz. And this one is exactly the other way around. It's z to the m plus 1 d by dz, z to the n plus 1 d by dz. And so this acts on phi left. That's the left-hand side. And now we know this is a carbon copy of what we did before. You see this picks up the term m plus 1 times z to the m plus n plus 1 d by dz minus n plus 1 z to the m plus n plus 1 d by dz. So that's what this is equal to. And therefore, this is equal to m minus n times the commutator of Lm plus n phi left, right? Because that's exactly how Lm plus n will act. So therefore, once you've determined that, you know already that the commutator of, so this must be equal to that. So therefore, we seem to be concluding that Lm with Ln will satisfy the width algebra. Right? Because the commutator of Lm with Ln acts like m minus n Lm plus n on any field phi. Was this too quick or is this clear? Yes?
I've got lost somewhere. So the middle line of the board is the...
So this is this term. Well, I have to calculate the commutator of this, right? So I have to calculate this minus the... so I have to calculate this this commutator minus this commutator, right? And therefore, I'm only picking, and then I'm picking out, no, sorry, no, not the commutator. So here I'm evaluating Ln on this. So this, the commutator of Ln with this gives you this. And then I'm evaluating the commutator of this. So this repeated commutator is equal to that, right? It's not, sorry, not a commutator. So this repeated commutator is equal to what I'd written. Because you see, the commutator of Ln with phi is z to the n plus 1 d by dz on phi. And now I have to take the commutator with Lm, but the commutator goes through dz to the n plus 1 d by dz, and then acts on this. So I get z to the n plus 1 d by dz, z to the n plus 1 d by dz on phi left. This is the first commutator. And this double commutator acting on phi has this form. And then I simply use the fact that now when I evaluate this, I have a term where this acts here, and I have a term where it goes through, and I have a term where this acts here, and I have a term where this goes through. Now the term where it goes through, the two terms cancel. So the only terms that survive is when the derivative hits here, and the derivative hits here. So this gives me an m plus 1 minus an n plus 1, and therefore gives me an m minus n, I mean the plus 1 just cancels, times the z to the n plus 1 d by dz, but that is just the commutator with Lm plus n. So I conclude that I can write this as m minus n times the commutator of Lm plus n with phi L. But on the other hand, the Jacobi identity tells me that this must be equal to that, so I conclude that the commutator of Lm with Ln is equal to m minus n times Lm plus n. So this indeed implements the conformal symmetry. But I've just cheated on you. Because, you see, this doesn't follow. I mean, I only know that inside a commutator with phi L, this is true. I don't know whether it's true as an operator identity. But what I know, it's true up to something which I shall call CMN. And CMN must be something that commutes with everything that appears in phi L. It commutes with all the AMs, it commutes with the Qs and everything inside. But this argument doesn't tell me that this term isn't there. It just tells me that this term must commute with everything else, i.e. that it is a central extension. Because you see, if it commutes with all the AMs and the Qs, then it will in particular also commute with the LMs, because the LMs are made out of the A's. So if the C commutes with all the A's, then it'll automatically commute with the L. So I know that I'm going to get an algebra like that, where this generator will commute with the L's. Now, obviously, I can try to calculate it, and I actually will calculate it for you. But before we do that, we can simply ask, what can CMN possibly be? And what we were going to do is we're going to play a game in using Jacobi identities and redefining generators to our heart's delight, so as to see what CMN can possibly be. Okay, so let's think about it. What can CMN be? Well, first of all, you see CMN must be antisymmetric in M and N, because the left-hand side is antisymmetric in M and N. So we know that CMN must be equal to minus CNM. That's just by virtue of the fact that it appears in the anticommutator. Now, the next thing we can work out is, let's ask ourselves, what about the Jacobi identity? Involving three L's. So the L's I'll take is LL with LM and LN plus, and now the cyclically commuted stuff, So that's the Jacobi identity. I know that that is going to be true. Now think about it. So the first time you put in this commutator, you're going to write this. This is going to become m minus n times Lm plus n plus Cmn, right? Now, because I'm going to take a second commutator, the C term doesn't play a role because, as I told you, C commutes with all the L's. So this term I can ignore because it won't contribute because C is central. But the second time I apply the commutator, I'm going to get a C term. So the Jacobi identity will give me the identity m minus n times C L m plus n minus L times C m n plus L minus m times C n L plus m must be equal to 0. So whatever these C numbers are, these central terms that appear here, they must satisfy this identity. Otherwise, they wouldn't satisfy the Jacobi identity. Otherwise, it wouldn't be a consistent Lie algebra. So I know that the C's will satisfy this, and I know they will satisfy this. Okay, but that's not all there is. I mean, so if you want to write this in sort of, say this in fancy language to impress your friends, you would say this is the closure condition. So this will turn out to be characterized by a cohomology, and a cohomology is closed stuff minus exact stuff, and that's the condition that it's a closed two-cycle. Anyway, that's just words. Now, why is this a cohomology? The origin for the fact that it's a cohomology is that, you see, you could also decide that you redefine your generators L by adding a central piece to them. So suppose you define new generators L hat n, and you define them to be Ln plus some operator Cn, which are also central. So when I say central, you should think of as being a number, right? So a number times the identity. So what about if I redefine my generators by adding to an identity? Now you would say, well, that's not going to do much, because if I calculate the commutator of Lm with Ln, well, this is the commutator of Lm plus Cm, Ln plus Cn, but the C's are numbers, so who cares? So they just go. Obviously, they're not going to contribute in the commutator. So this is just the commutator of Lm with Ln. So this is equal to m minus n times Lm plus n plus Cm comma n. But now, you see, we want to rewrite the right-hand side also in terms of hatted generators. So here we have a hatted generator, here we had a hatted generators, but here we have an unhatted generator. So this means we want to write this now as m minus n times L hat of m plus n minus C of m plus n, right? Because the unhatted generators are the hatted one minus C of the mode number plus Cm comma n. So what we learn from that is that this transformation, this modification, this new definition of our L hat variables modifies the central term, because the new central term, now we have the form L hat m, L hat n. Well, this is still equal to m minus n L hat m plus n, but the central term is now the old central term plus a minus m minus n times C m plus n. And this combination is what we're going to call C hat m plus n. So as you see from that, by redefining the generators in this seemingly trivial manner, you actually modify the central term, because you can modify it by subtracting from it m minus n times any function that's only a function of m plus n. That's the exact piece of the cohomology. That's the freedom of adding an exact form and redefining it. So the question is, how many closed forms are there modulo exact forms? Or put differently, how many different CMNs are there that you can't absorb in that manner? And you see, when you say that for finite dimensional Lie algebras there are no central extensions, what you mean by that is you can obviously write down central extensions, but you can always undo them by simply redefining the generators in that manner. You can set it to 0 upon a slightly more clever choice of your generators. There's no real extension there. There's no real central, there's only stupidity. I mean, if you choose your generator stupidly, you get punished, but it's your choice to get punished, right? You can always define the L hat so that the central term goes away. That's the reason why for SU2 and SUN and E8 and whichever Lie algebra you've ever dealt with in your life, you've never seen a central extension because somebody has thought about it and found a clever choice that removes all of these stupid central terms. Now, for the Virasoro algebra, as I'm about to show to you, you can't do that. You can't get rid of it, but you can use this choice to bring the central term into a specific form. So let's think about what are clever choices for how we choose this. So now we make a number of choices for these redefinitions. So we choose, now I have to look up, we choose, so we make a choice. So choose Cn, and I hope I've done this the right way around. Okay, that looks good. Choose Cn to be of the form Cn, 0 over n for n not equal to 0. So that's the first choice we do, and then we choose C0 to be equal to a half times C1 minus 1. So this is the thing that appears here, right? That's the C with 1 index. So we make a choice like that, and let's work out what the new central extension will look like. And what I claim is that that removes all the central terms of the form n0. So I now claim that Cn0 hat. So after I make this choice, what is Cn0 hat? Well, Cn0 hat is Cn0 minus n minus 0, so minus n times Cn. And you see, with this choice of Cn, n times Cn is just simply Cn0. So what this means is that I've set all the central terms where one of the labels is a 0 to 0, right? So that's what this choice accomplishes. I can always choose these central terms to be 0. And what does this one accomplish? Well, this accomplishes that C1 minus 1 hat. What is this? This is the old C1 minus 1 minus 1 minus 1 minus 2 times Z0. And I've chosen the Z0 in such a way that the C hat 1 minus 1 is also equal to 0. So but now I've used up all my choices, right? Because I've picked Cn for all the non-integers n, and I've picked Z0. So I can use this to make sure that the C hat n0 and the C1 minus 1 are equal to 0. But I've used up now all my freedom, right? I have no more freedom in choosing these redefinitions because I've just fixed them for all of them, and I've used it up so that these central terms and this central term is equal to 0. So now what we do is we ask what remains for the central terms. Well, we still have to solve the Jacobi identity. So one thing you can easily convince yourself is if the C satisfy this identity in the box, then the C hat will also satisfy it. That's sort of more or less hardwired, but you can also just plug it in. I mean, so I leave it as an exercise to you. This definition, if the C's satisfy the boxed equation, then these guys will also satisfy the boxed equation. It's not totally obvious, at least not to me, but it is true. I mean, you will find out that it is true, but it requires a little bit of effort. But anyway, it is true. And now what we're going to do is we're going to use this identity for the hatted ones. So now we've gone to the hatted ones. So for the hatted ones, also this is true, right? This is what I've just said. And now we evaluate that equation for L equal to 1. So let's look at that equation for L is equal to 1 and for N is equal to minus M minus 1. I mean, this is true for all L and M and so on. So let's just plug this equation in for L is equal to 1 and N is equal to minus N minus 1. You see the first term, what happens to the first term? If n is minus m minus 1, this becomes minus 1, this becomes 1, but we know already that c hat 1 minus 1 is equal to 0. So this term will disappear for this choice of L and n. So I have to deal with that term. So what is that term? So that term is minus m minus 1, n minus L minus 1 times c hat of, what is this? This is m. So this is another, okay, I keep m fixed. And then n plus L is minus m, right? So this is this term. And this term is plus 1 minus m times c minus m minus 1. And then over here, it's m plus 1. So that's the identity that comes out of the Jacobi identity for these c hats, right? It's just applied this for this choice of L and n, and what I've used is that c hat 1 minus 1 is equal to 0, and therefore they are not, kills this term, and therefore only these two terms survive. Now look at this. Now look at this equation. You see, this equation I can bring into slightly more beautiful form. I'll bring this to the other side. So then this will be c, and then I bring this to the other side by inverting the. I mean, this is antisymmetric, so this picks up a sign, it picks up another sign. So cm plus 1 minus m plus 1 times 1 minus m is equal to minus m minus 2, so maybe I write this as m minus 1, then I have another minus sign, is equal to minus m minus 2 times c hat m comma minus m. So if I change signs, what I find is that m minus 1 m minus 1 on m minus 1 times c m plus 1 minus m plus 1 is equal to m plus 2 apply on times c m minus m. So this is one identity I get. And you see that's a recursion relation relating c m plus 1 minus m plus 1 in terms of c m and minus m. Right? So this is sort of the next step up. So this gives me a recursion relation for all the c's where the mode numbers add up to 0. And in fact, the other equation is so the other identity that so this is one choice. So the other choice is by taking L to be 0 here. So if I apply this for L is equal to 0, then you see this term is equal to 0 because I've set all the c hats involving one mode number being equal to 0 to 0. So this guy is 0. And again, what I get is I get n minus L. So I get n times c hat of n of m comma n minus m times c hat of n comma m is equal to 0. That's the constraint I get from applying L is equal to 0 to this identity and using that this term is equal to 0. So you see this equation, what does this equation look like? You see this is antisymmetric, so this is the equation m plus n times c hat of m comma n is equal to 0, right? Because if I turn this around, I pick up a minus sign, so I get n plus m times c m comma n is equal to 0. So what does this equation mean? Well, this equation means c hat can only be non-zero if the mode numbers add up to 0, because if the mode numbers add not up to 0, then obviously c hat of m and n must be equal to 0. So what this implies, that c hat of m comma n must be proportional to delta m comma minus n, because otherwise this identity can't be true. And then this identity gives me a recursion relation for what the different CMs must be expressed in terms of one another. And if you stare at this, it's clear what the answer to this recursion relation is. Cm comma minus m must be equal to m plus 1 times m minus 1 times some constant times delta m minus n. Well, this I know already, so okay, this I don't have to write because there is no n here. So I'm just evaluating it on those that because you see, when you make m1 bigger, then you haven't got the term m plus 2 yet, but you're losing the last one, right? So when you make m1 bigger, then this term is missing on the left-hand side, and the m plus 2 term is missing on the right-hand side. So this recursion relation basically tells you that C hat of m and minus m has to be of that form, where this is some number, which is some number, right? It just tells you that this is true. This you can take, well, actually, you can think about it. What is it for 2? For 2, this is 3 times 2 times 1. This is 6. So this is C2 comma minus 2 over 6, right? So what this tells you is that the C hats are 0 unless the mode numbers add up to 0, and they're all determined by the coefficient of C2 minus 2, and they're recursively determined by the coefficient C2 minus 2 by this formula. So that explains to you why the central term that appears here, after redefining my generators, is necessarily of this form. Because I've just explained to you that I can always bring it into this form. And by bringing it into this form, I've basically used up all my freedom in choosing these redefinitions that I've explained to you here. So what this tells you is that there is no further freedom left, and therefore either this coefficient is 0, in which case all of them are 0, or this coefficient is not 0, then all of them have this form. And this coefficient you tend to call C over 12 for historical reasons. So what I've just shown to you is that we know, purely based on abstract DUDA, abstract Jacobi identities of Lie algebras plus redefinition freedom, we know that the term that appears here must be of the form plus C over 12 times m squared minus 1 delta m minus n, because that's the only game in town. I can always bring it into that form, and so that must be the algebra I get. I should say that in doing that, I've assumed that the L0 generator with Ln doesn't have a central term, and the L1 and the minus 1 generator have this property. And you can check for this ansatz that I've written down that this is indeed true. So we know that for the Lm's that we've written as normal ordered products of the An's, we know that the answer must be of this form. So now that we know what the answer must be, we can simply calculate one simple commutator to determine this potential term, and then it's either there or it's not there. And if it's there, then that's what it is. And if it's not there, then all this beautiful discussion about what could have happened hasn't materialized. I've just bored you for the last 20 minutes. Well, it's some useful fact maybe for your future mental health, but it's not particularly relevant for anything I'm about to do. Well, it is, otherwise I wouldn't have explained it to you. Okay, so now what's the easiest way of checking what this central term is? Well, the easiest way of checking it is simply to evaluate the generator, these generators on some ground state in the Fock space. So the simplest way of doing it, you see, is to, so if we work on the state where k is equal to 0, you see, we know that L minus 1 on this, remember, L minus 1 is a half times the sum over n, the normal ordered product of A minus 1 minus n A n. Okay, so I have to have two modes that sum up to minus 1. And I know that positive modes kill here. So what's the best I can do? Well, the best I can do is I take one to be a 0 mode and the other one to be a -1 mode. I can also take one to be a +1 mode and one to be a -2 mode, but that's even more deadly. So the best I can do is the 0 mode, but the 0 mode also kills that. So I know that this is equal to 0. Okay, so what's the first non-trivial term? The first non-trivial term is the L-2 term. So in the L-2 term, I write down the same sum. So now it's A-2 minus N, A-N. And now there's one term that will survive, right? Namely the term where both the mode numbers are equal to -1. They have to add up to -2. I can't use a 0 or a positive mode. I'm only allowed to use negative modes. So the only choice I have is to pick the term where n is equal to -1. So I learned that this is equal to A-1 on the vacuum, right? So L-2 on the vacuum is not equal to 0. Okay, but now if I want to calculate the commutator of L2 with L-2, well, I know that L2 on the vacuum is 0 because you see for L2, these mode numbers have to add up to +2. So at least one of them has to be positive. So boom, that kills the vacuum. So I know that L2 will kill it. So this is going to be equal to the commutator. The commutator of this will be equal to 4 times L0 on the vacuum plus C over 12, 2 into, well, this thing here, right? C over 12, 2 into 4 minus 1 is 3. So 2 times is C over 2 times the vacuum. Right, so, but on the other hand, L0, what is L0? Well, they have to add up to 0. So either one is positive in which I die, or both are 0, but 0 also dies, so also 0. So this term is 0. So I know that this commutator is just equal to C over 2, but I don't really have to write a commutator. I can also just write the operator, because if I reverse them, then it's also 0. So what I have to do is I have to evaluate L2 on this state, and that will tell me what C is. Okay, so I just evaluate this C2, L2 on a half times A-1 on the vacuum. What is this? Well, I have to commute through L2 past this, so this is equal to a half times the commutator of L2 with A-1 on A-1 on the vacuum, plus a half times A-1 on the vacuum times L2 A-1 on the vacuum. Okay, and now remember, what is the commutator of the Ln's with the A's? The Ln's with the A's are minus the mode number of the A times A of the sum of the mode numbers. So this is equal to A1, and this is equal to A1. Okay. Now, obviously, the second term is 0, then because A1 kills the vacuum, so that dies. And here, okay, because A1 kills the vacuum, I can replace it by the commutator of A with A1 with A-1. What's the commutator of A1 with A-1? That's equal to 1. So therefore, this is just equal to a half. So therefore, I know that this coefficient is equal to a half, and therefore I conclude that for this free boson theory, the central charge is equal to 1. And as you see, there was really nothing I can do here. This is not this comes just out of the box. I have no choice but to get that, right? I get a Virasoro algebra, and the Virasoro algebra comes with a definite value of this central term, and the value for the central term for one free boson is equal to 1. Is that clear? Now that's the cheap and dirty way of doing it. So let's do it the honest way. Now what's the honest way? Well, the honest way, yes.
Why did you get the commutator?
Which commutator? This one? Well, so this is equal to the commutator plus the operators in the opposite order. But the L2 on the vacuum dies because L2 on the vacuum is made up of two modes whose mode numbers add up to +2. So at least one will be positive, so that kills. Any other questions? Okay, so this is the user-friendly way of calculating the central charge, but we are not here to be user-friendly. So what would be the honest way of calculating the central charge? I mean, it's always good to do a calculation in more than one ways, in particular if it's an important calculation, to make sure that you've really done it right. Yes?
Why is it that we ended up in this homology class where you just have C and not other?
Right, so I skipped over that, but what I argued was that my definition of Ln, which is a half into the sum over L A n minus L A L, I claimed that is of the form that, well, what you see is that, so what I claimed is that you can easily calculate that Ln on Ln is equal to minus n times Ln. Because you see, when you move this through, I mean, I didn't quite show it, but you see, if you take this to be 0, then it's, then if you move it through, you see that you just pick up minus n times Ln. So therefore, you know that the term Cn comma 0 or 0 comma n is 0 for this choice of generator. And furthermore, I showed to you that L1 and L minus 1 annihilate the vacuum. And because L1 annihilates the vacuum and L minus 1 annihilates the vacuum, it follows that the commutator of L1 with L minus 1 annihilates the vacuum. But that is going to be 2L0 plus C1 comma minus 1. And therefore, because L0 annihilates the vacuum, you also know that C1 comma minus 1 is equal to 0. So I'm exactly in the gauge choice that I worked out. And therefore, I know that my central term has to have the canonical form. And then I can simply calculate it by doing this one calculation. It's clear? Yes? Say again? Right, so this is for one real scalar field, yeah. So if you have two real scalar field or one complex scalar field, you will have C equals to 2, yes. So there you would have generators A and A bar, I mean, A and A complex conjugate, if you, I mean, it depends on how you write it. But you get for every real scalar field, you get a C equals to 1 here. Okay, so as I said, this is the, I mean, this is the user-friendly way of doing it. But you see, we've written down a formula. I mean, we shouldn't be such softies. We should just work it out. I mean, what's the big deal? We just write down Lm with Ln. So why don't we just work it out? I mean, we've written down here the expression. Why do I pussyfoot around this in a way to avoid this, to deal with this? I should just take this at face value and work out the commutators and get what I get. Now, the issue is there are infinite sums here. And you have to be a little bit careful how you do these infinite sums. And the smart way of doing this infinite sum, so the other thing I should say is that obviously this term is unambiguous unless n is equal to 0. Because if n is not equal to 0, then these mode numbers never add up to 0, and therefore there's no ordering ambiguity in how to write them. So the only tricky bit is the L0 term. So therefore, I have to worry about the commutator that ends up with an L0 term or that involves an L0 term. So let's just get a sense for how this calculation works. So if m plus n is not equal to 0, then this calculation you can actually do relatively easily, because you see we know already that Lm with an is equal to minus n times am plus n. So what we can do is we can let one Lm standing and replace only one LL by a double sum. So we can write this as a half into the sum over L, and then we write this as Lm with the normal ordered product of n minus L with AL. Right, and this we can work out, and you see what we are going to get are terms that are being, okay, let's write out the first term. So we are going to get this with this, will give us L minus n times am plus n minus LAL. Right, this is what I get from the first term, and the second term will give us minus L from the second guy, a times n minus L, am plus L. Right? This is what you get when you calculate this commutator. Okay, so here I've picked the specific order, but you see the order doesn't matter as long as m plus n is not equal to 0, because the order of these things doesn't matter unless the mode numbers all add up to 0. If the mode numbers don't add up to 0, there's no ordering ambiguity. So I don't have to worry about it. So now I want to bring this into standard form. So here I have to change variables. So this wants to be called L again. So I define L hat to be equal to M plus L. So then L is equal to L hat minus M. And therefore I can write this as a half into L minus N, A M plus N minus A L, minus, and this L I replace by that. So this becomes a plus M minus L hat. So this is now as, maybe I should write it as a double sum, plus a half times the sum over L hat. And this minus L becomes M minus L hat. And then it's A M plus N minus L hat, A L hat. Right? So this is what the second term becomes after I've redefined it. This is the first term written out again. And then obviously this is a dummy variable, so now I can erase the hats. And then I see that these two terms just combine into M minus N times L M plus N. So all is well for unless M plus N is equal to 0. That's just another way of seeing that this central term can only appear if the mode numbers add up to 0. Otherwise, there can't be a central term, at least not in this incarnation. In this incarnation, there is definitely no central term unless the mode numbers add up to 0. So now I can simply, so now I only have to worry about a case where M plus N is equal to 0. And this calculation I can do honestly. I just have to be a tiny little bit careful. And that will tell us what the origin of this central term really is. That's the reason why this is an important calculation. I mean, at the moment, we've learned about it in some sort of roundabout way. We found out what it is, but we don't really know why it appears. We haven't got an intuition where it comes from. So let's gain an intuition where it comes from by working out Lm with L minus M. And let's assume that M is positive. I mean, without loss of generality. I mean, that's the only term where this matters, where the sum is not equal to 0. And let's write the second term in normal ordered form. So obviously it doesn't, on the face of it, it doesn't matter, but I will have to reorder infinitely many terms unless I start writing this in normal ordered form. So you will see in a second why this is important. So I can write this as a sum over L bigger than 0. So I write out the second Ln, the L minus M I write like that. And I write it as a sum over L. And I write it as A minus N minus L, AL, plus A minus M minus L, LM with AL, right? This is the terms that I get from having, so do you see what I'm doing, or this is too quick? I mean, I'm writing L minus M as the sum, and I've written out the terms for L positive, then AL is to the right of AM minus M minus L. And then the other term is plus a half times S less than 0. And for these terms, obviously, these are in the opposite order. So then in the opposite order, the first term is LM AL, A minus M minus L, plus AL, the commutator of LM A minus M minus L. That clear? So now I've just written out the commutator honestly. No indirect complicated argument, just so my supervisor always told this story that when he was a student, he went to some lecture and some guy gave some super complicated analysis, and then a guy in the audience raised his hand and said, but can't you use group theory to make this much simpler? And then the guy at the blackboard said, strong men don't need group theory. Now, I certainly don't want to advocate that point of view, but this is sort of a little bit that I mean, here I'm just going with the head through the wall, but the advantage is that you see where this comes from. I mean, my point is that you should see it comes from a normal ordering ambiguity. That's the point of this calculation, to see it with your bare eyes that this comes from a normal ordering ambiguity, and you'll see it in a second. And you'll calculate it, and we'll get the same answer. So that's an important consistency check. Okay, so now we've written this out. So now we can simply work out all the terms. Okay, so what do we get? So here we calculate. So we get a half into the sum L greater than 0. This commutator will be m plus L times A minus L AL, right? This is what I get from here. And then from here I have plus A minus M minus L, and then I have A M plus L. Right, this is what I get from these two terms, simply using, sorry, I've forgotten times minus L. Right, this commutator gives me minus L times A minus M minus L, A M plus L. So that's the first line. And the second line, what's the second line? Well, this is plus a half into some L less than 0. And here, what do I get here? Here I get minus L into A M plus L, A minus M minus L, plus, and then I have to get the minus this, so this gives me plus M plus L times AL, A minus L. Right? So that's what I get when I just work it out. And now you have to stare at this. So now we would like to think of this as being the normal ordered expression that it wants to be. So now we would like to express all of these terms in terms of normal ordered products. And so this is like this game for little children. Now you have to spot the difference. Which of the term is bad? There's one term that's bad. 3 terms are good. 1 term is bad. So let's check. So this term, L is positive, AL stands to the right of A minus L. This is a good term. Here, AM plus L stands to the right. M is positive, L is positive. So this term is good, this term is good. This term, L is negative. A minus L stands to the right. This term is good. This term, not good, right? Because M is positive, so minus M is negative. Now L is also negative, so for sufficiently many negative L, this becomes in the right order, but there are finitely many terms that are in the wrong order, namely for the L's that go up to M minus 1. So this is equal to the normal ordered term, and the normal ordered term will just turn out to be 2M times L0, the normal ordered L0, plus a piece that comes from reordering this term for finitely many terms. And what you get is plus a half into, okay, so this is begins its life as L from minus M plus 1 up to minus 1 of minus L times, and now I have to put in the commutator of A M plus L, A minus M minus L. Right? I mean, the rest is normal ordered, and when you work out the coefficients, it just gives you the normal ordered L2M L0. That's not a tricky bit. And what's left over is this term for the L's where this is in the wrong order, and this is in the wrong order if L is negative and goes up to minus M plus 1. Because for minus M plus 1, this is just minus 1, right? So the minus 1 should have been to the left of this one, so I have to reorder it. For 0, it doesn't make a difference. Then 0 times 0 is 0 times 0. It doesn't make a difference. For the more negative L's, it'll be fine, but for finitely many L's, it goes wrong. But this sum, you see, is easy, because so this I can write as plus a half. Now I change L from 1 to M minus 1. And then, so this becomes then an L, if I change L to minus L, and this becomes M minus L, right? I mean, this is equal to M plus L, right? Because that's the commutator of A something with A minus something is something. So this is M plus L, but I'm changing from L to minus L, so this becomes L into M minus L. So now is the moment to open your Mathematica notebook or just think about it. So now you can work this out. And when you work this out, you find that this is equal to this term. This sum is exactly equal to 1 over 12 m into m squared minus 1. So, I mean, it's a finite sum, right? I mean, it's not rocket science, but it's obviously, so the linear term you all know, right? The sum over L, you know, that's Gauss. The sum over L squared you have to look up or work a little bit. You know, I mean, you know, the sum over L squared will be a cubic because it's like integrating. So you have to work out 4 terms and then write down the most general recursion, most general ansatz, fix the coefficients. Okay, I'm not going to do it for you, but you can work it out. It's not rocket science. And when you add them together, you get exactly this expression. So this is the sort of first principles way of deriving the central term. And then what it makes clear to you, it comes from this funny normal ordering ambiguity. It comes from, it's a quantum effect. It's something that comes because in the quantum theory, your operators are normal ordered. And when you commute them, they sometimes end up not being in the right order. And you have to reorder them. And the reordering term is the central term. So the central term is a reordering term from a typical quantum computation. You should think of this as being proportional to h bar. It's sort of a quantum effect, and that's how the classical conformal symmetry, which this theory has, gets broken in the quantum theory. It picks up this anomaly, and the anomaly gets picked up like all quantum anomalies are. It comes from some ordering prescription type ambiguity. So this has now explained the free boson to you in as many ways, probably more ways than you wanted to know. But here we go. And so this is, so how much time do I have? I have another half an hour or so? Okay. Okay. Okay, so are there any questions about that? Or is that, are you bored with bosons by now?
Suppose you wanted to do quantum quantization, would it be easy to compute the central charge there?
Not sure. I think then you get into the thorny issues of your measure and stuff. I mean, I think this is the, certainly as far, well, I mean, I've given you 2 arguments how to calculate it, and they're both explainable within an hour on a small blackboard, so I think you shouldn't complain. Any other questions? Okay, so in danger of beating a dead horse even more, I don't want to talk about bosons anymore, but I want to explain to you the free fermion, because there's actually a new feature that happens in the free fermion, and that'll be important to see when we discuss the free fermion, because it'll be the segue into what more general fields will look like. And that has to do with the fact that the free scalar field has basically conformal dimension 0, so it transforms in some sense like a scalar under conformal transformations, but the fermion doesn't. The fermion has a conformal weight, and as a consequence, some of the identities that we'll see will get modified in an interesting way, and it'll be useful to see it. I won't quite go into quite the same level of detail. I won't bore you with an analogous calculation, although you could do it, but I want to explain to you at least some of the features that are different when you deal with fermions. Okay, so the second example is the free fermion, the massless fermion. So here the Lagrangian density is simply a half into psi transpose gamma 0, gamma mu, d mu psi. So the gammas are 2-dimensional Euclidean gamma matrices, so they have to satisfy gamma mu is equal to 2 delta mu nu because we are in Euclidean signature. And then you can pick them to be gamma 0, you can pick to be 0, 1, 1, 0, and gamma 1 you can pick to be 0 minus I 0. That's one choice. And your fermion will be a 2-component fermion, psi and psi bar. I mean, I called it psi and psi bar. And this is just a transpose which turn a column vector into a row vector. And then if you write this out, then you see what this becomes. This expression becomes simply d0 plus I d1. You see the gamma 0 will basically, so So the gamma mu's are all off diagonal, and when you multiply with gamma 0, you bring them to be diagonal. So gamma 0 squared will be 1, so you will have a d0 on the diagonal, and gamma 0 times gamma I gives you a minus I, so there should be a minus I here. No, it's a plus I. Oh dear. Oh no, it's a plus I. It's because this one gives you a plus I, but you have a minus I down here. So this is how this acts on psi bar. And therefore, if you write it in complex coordinates, what you see is that this becomes, in terms of z's and z bars, the Lagrangian density becomes simply psi dz bar psi plus psi bar dz bar psi and plus psi dz psi bar. So that's what this becomes, right? Because the first component, which psi, is the derivative. I mean, remember, dz bar is equal to d0 plus I d1, and dz is equal to d0 minus I d1. So the lower component is the dz, the lower component acts on the psi bar, so you get this term and this term, and the equations of motions are as easy as they get. They're simply that psi is holomorphic, so dz bar of psi is 0, so psi is holomorphic, and dz of psi bar is 0, so psi bar is anti-holomorphic. And then we can write down a mode expansion, and the mode expansion will write down, and in the following, again, I concentrate on the left movers, on the psi's. The psi bars work the same way, and it's convenient to choose some funny normalization. It doesn't really matter. And then you have a sum over S, and then the modes are called B. It's Bs times Z to the minus S minus a half. Now, why I put the minus a half here is a secret I keep for me for a little bit. But I'll just, I mean, I'm obviously free to write whatever I want as the exponent. I just have to explain to you what values S takes. So in order for this to be single valued, S wants to be in a half integer. So I'm going to sum here over half integers. And then this is again single valued. It's just a Baroque way of writing a mode expansion with integer exponents. But for reasons that will become clear relatively soon, this is the smart way of writing it. And this is what you would normally call a Navier-Schwarz fermion. So a Navier-Schwarz fermion is single valued on the complex plane, whereas in the Ramond sector, you would choose S to be integer, then the fermion would pick up a minus sign as it goes around the origin. Now you see, for fermions, picking up a minus sign is something which something a gentleman can do, because fermions never come alone in life. Fermions never can, I mean, you always have two fermions, and therefore, if a single fermion picks up a sign as you take it around, okay, so be it. Just two fermions have not allowed to pick up a sign, so you have two choices, whether the fermions are periodic or anti-periodic. The sector where the fermions are periodic on the plane is called the Navier-Schwarz sector, and the sector where the fermions are anti-periodic on the plane is called the Ramond sector, but I won't be talking about the Ramond sector for quite a while. In fact, from a CFT point of view, fermions are really Navier-Schwarz fermions, and the Ramond sector is a bit of a headache, which I'll come to at a later stage. Okay, so then we have to impose some, so this is as before, and we can do the same thing for the right movers. Then we have to worry a little bit about what the canonical quantization rules are. But before you worry about that, you should note that there is one important difference to what we had for the bosons. So if you look at this Lagrangian density, the action we have to integrate against dz and dz bar. And let's look at the first term. The first term is psi dz bar psi plus the other one. Now, we want this to be scale invariant, because this is meant to be a conformal field theory. And obviously, with respect to the z bar variable, it's nicely scale invariant, because you see, you have an integrand, you have a measure, and you have a derivative. So when you rescale the z bar variables, this one scales the opposite way than d by dz. I mean, you know, d by dz is basically a dz in the denominator and a dz in the numerator. If you scale them simultaneously, their scale factor will go away. So the dz part is fine. But what about under the transformation of z? Well, under the transformation of z, you pick up a factor of lambda from here, but seemingly this is not compensated by derivative. This is to be contrasted with the case for the boson. Remember the case for the boson, there the action was dz phi, dz bar phi, right? And there everything was good. The d by dz balanced the dz, the d by dz bar balanced the dz bar, so this was nicely conformally invariant. Now, what about this one? So on the face of it, you would say, okay, this is not conformally invariant, because when I rescale the z variable, I pick up a factor of lambda from here, and I pick up nothing from here. Now, that is if you assume that the fermion is inert under a conformal transformation, just like the boson. You see, the boson doesn't do anything when you conformally transform it. The derivatives make sure that the boson doesn't want to do anything for the action to be invariant. So what this tells you is that under a conformal transformation, you have to rescale the fermion by a factor that's proportional to the square root of the scale factor, because there are two fermions, right? So each fermion will pick up a factor of lambda to a half, or lambda to the minus a half, so as to compensate the factor of lambda that comes from the change in measure. So what this means is that so in general, psi of z, if you go to if you rescale your coordinates, if you apply a Möbius transformation, it will pick up the factor of zeta prime of z to the a half times psi of zeta of z. So this is the important difference to the boson. These fields transform with this funny prefactor that guarantees that the action is conformally invariant under a Möbius transformation, at least. And this is what you call, so this exponent is what you call the conformal dimension. So what you learn is that in order for this to have a chance to be conformally invariant, you have to assume that the conformal dimension of the fermion is equal to a half. And this can simply be read off from this action based on the purely scaling argument to see how does psi have to transform so that the thing stays invariant under a scale transformation. Now you cannot worry whether it's true under an arbitrary conformal transformation, but you see it'll also be true under an arbitrary conformal transformation, because you see this will pick up two factors of d zeta by dz, and therefore will give you together a factor of zeta prime z, and zeta prime z dz will give you d zeta. So therefore this will be automatically correctly transforming as long as the psi transform that. So this must be the correct transformation of the fermion if the fermion is to be conformal. So for this theory to be classically conformal, you have to assume that the fermion transforms in that way so that this action is invariant under Möbius transformation or local conformal transformation, or whatever you want. But certainly you need a factor of that kind, otherwise you have no chance. Okay, so this is important, and that has an impact at various places. So it has an impact in writing down the correct canonical commutation relations, because it affects the conformal transformation from the cylinder to the plane. There's a factor that comes from this, but I don't really want to go into that. That's probably something that's not, maybe that's not that important for what we are going to do in the future. But it is important for understanding what the, so I'll just state what the correct canonical commutation relations are. Well, there are going to be anti-commutation relations because the canonical commutation relations, you have to be a little bit careful. There's a small subtlety here, but I don't want to bore you with details that are, because I think you'll believe me the answer anyway, because if you have read any string theory book, you've seen the answer, so you'll probably be willing to take it at face value. But you have to be a little bit careful how this comes from an equal time commutation relation. And this has to do with the fact that you have this factor of a half from the conformal transformation from the cylinder to the plane. But don't worry about it. So the canonical commutation relation leads to that anti-commutation relation for the B's. And then we have a Fock space as before. And then we can also work out what the T minus minus component is. Remember, that's going to be where the L generator should come from. And the T minus minus is going to be a half into T00, a minus I times T10, as before. And then what you find is that this just is a half into psi bar times the D0 minus I D1 times psi bar plus a half into psi D0 minus I D1 times psi. And then using the equations of motion, namely that this is equal to 0. This means the first term goes away. And what you get is that this is equal to psi dz psi. So that's the T minus minus. And then given that we have expanded out psi in this form, so this we are going to write again as the sum over n, ln z minus n minus 1, n minus 2. So now we have to plug in this formula. So you see now we have a term that goes like psi dz psi. So we have to calculate also what dz psi is. So what's dz psi? Well, dz psi is minus 1 over square root of 2, sum over all s in half integers. And then we pick out a factor of s plus a half. And then we have bs. I mean, bs is not to be the bs you're thinking of. It's b with mode number s, z minus s minus 3 halves. And then if you take this one and you multiply it with this one, then you're again going to get stuff that goes like mode number plus mode number minus 2, the minus a half and minus 3 half assemble into the minus 2. And what you learn is that ln has the form of being equal to, and now I better check that I write it down correctly. It's a half into, there's a minus sign here that absorbs this minus sign. And then it's a half into the sum over r in z plus a half. And then it'll be bn minus r, br, and then you have a factor of r plus a half. So this will be the formula for the stress, for the modes of the stress energy tensor that you get for this fermion theory. And you see this factor of r plus a half comes from the fact that you have a derivative here. This derivative produces for you this term, and that's the term that gives you this contribution to the modes of the stress energy tensor. Is this clear, or do I have to write it out in more detail? Okay. Okay, so now we also normal order this. So we write normal ordering here in order to make this into a normal ordered expression. Now normal ordering here for fermions means the same thing. Positive modes want to stand to the right of negative modes, but if you invert them, you have to pay the price of a minus sign because they're fermions rather than bosons. So it's what you've seen in QFT. And the other thing you may observe, you see the term, this a half term, doesn't actually matter because this is antisymmetric in r goes to n minus r. So the piece that doesn't involve r doesn't matter. So I can also erase this term because this term, once I do the sum, sums to 0 because the terms where r and n minus r interchanged contribute with an opposite sign and therefore cancel out. So this is the form of the stress energy tensor for the free fermion theory. And now we can try to imitate what we had before. So we want to understand what this does, how this acts on the fermion field. But now we know life will be a little bit more complicated because the fermion has this funny conformal dimension factor. So this is going to modify how Ln will act on the field. Because you see, previously, for the boson, we didn't have this factor. When we changed coordinates, there was no effect from the conformal scaling dimension of the field, but now there is. So there will be an additional contribution. And in order to understand the nature of this additional contribution, that's one of the main motivations for doing this admittedly slightly sketchy calculation. Okay, so what we have to calculate again is Ln with BR. right? Because the psi field is made out of modes Bs, so we want to know what Ln is with, let's say, Bs. And Ln is this normal ordered product, so this is going to be a half into sum over R. R is half integer, and then we're going to have the anti-commutator, the commutator of Bn minus R Br with Bs. But again, and we have this factor of R here. That's important. This factor of R, that's what is going to, where all the fun is going to come from. And then again, the normal ordering will not play a role because as we commute it through, the anti-commutator is just a number and it doesn't care in which order it stands. So what do we get? We get a sum, a half, then we get a sum over R, then we get Bn minus R, and the anti-commutator of R with S, so this gives you delta R minus S, plus, or rather minus. You see, once I've moved this through, I pick up a minus sign, and then I have this anti-commutator, so this gives me delta n minus R comma minus S dr. Right? So this is what I'm going to find. Is this clear what I'm doing? I mean, I'm just moving it through. So this is this term. When this goes past this, and then when this goes past this, this is this term, right? And whether I write a delta to the left or to the right of the B doesn't matter because it's a number. So now I can evaluate this. So R is equal to minus S. So what do I get? So out of the sum over R, only the term R is equal to S survives. But so this will go like Bn plus S. So R is going to be minus S. So minus R is equal to S. So R is equal to minus S. So from the first term, I get a minus S over 2. This is what I get from this piece, right? R is equal to minus S, and I have a half outside. And then from here, this R is going to be equal, this means that R is equal to N plus S. So this R is going to be equal to N plus S, so this gives me minus N plus S over 2. So that's the commutator of Ln with Bs. So this is of the form, this is minus S times minus N over 2 times Bn plus S. So that's the commutator of Lm with Bs. So you see this term looks exactly analogous to what we had for the boson. Remember, Lm with An was minus N times Am plus N. So this is the term that looks like the boson. And this term, you see this half wants to be that half. So that half, as we'll see in a second, comes from the fact that we have a conformal factor. And so that's the important correction term that arises because the fermion has an intrinsic conformal transformation behavior that's characterized with conformal dimension, a half. So how can we see this? Well, now we can work out how this, now we can see how this Lm acts on psi, right? So what is Lm on psi? Well, so we simply write down the sum. So we have 1 over square root of 2. Then we have the sum over S in Z plus a half. Then we have Z to the minus S minus a half. And then we have the commutator of Lm with Bs. And what this is going to be is equal to minus S minus N over 2. Oops. Sorry, this should be an N. So then maybe I'll also call this an N. So then this is minus N over 2, B of N plus S. And now I want to bring this again into standard form. So I want to, this mode number wants to be an S hat. So S hat is equal to N plus S. So S is equal to S hat minus N. So if I want to write this in, now I want to write this as a sum over S hat. Obviously, N is an integer, so S hat is still a half integer. So then what does this prefactor become? This becomes minus S becomes N minus S hat minus a half. This becomes minus S becomes N minus S hat minus N over 2 times B n S hat. Right? So one term looks vaguely good. So what we would have thought is that that should be equal to z to the n plus 1 d by dz on psi, right? Because that's how the Ln is meant to act. So what would have that been? Well, if we calculate that, that would have been 1 over square root of 2 sum over s in z plus a half. So I'll simply take the derivative with respect to s. So I would get a term that looks like s plus a half, or rather it looks like minus s minus a half, right? This is what I get from the exponent. And then I get bs times z to the n minus s, right? N minus s minus a half, right? That's what I would have gotten from the. That's what I would have gotten from the. I think I've done something wrong, but. Okay, that still looks good. Ah, yeah, sorry. I mean, this is a stupidity. I should write this as n over 2 minus s, right? Okay, so you see, this looks like, now I can put things together, and I can read off what's the correction term, and then we'll understand why the correction term is what we should have expected. So therefore, Ln with psi s, with psi of z, is equal to z to the n plus 1 d by dz of psi of z. This gives me, okay, so this accounts, so the minus s term accounts for this minus s term. And then I've left over a minus a half. So I want to write this as s minus a half. And then I should write this as n plus 1 over 2. So what this means is that there is a correction term, and the correction term goes like plus a half times n plus 1 times z to the n psi. So if I write this in sort of combined, this is plus a half times n plus 1 z to the n acting on psi of z, right? Because the first term just gives me the minus s minus a half, and then the rest is plus n plus 1 over 2, but it also has increased the exponent by a power of z to the n. So this is apparently the way this field transforms under the commutator with the Virasoro generator, the Virasoro generator being analogously produced out of my free field. Now, why is this what I should have expected? Well, the reason why this is what you should have expected is because of the funny conformal transformation formula. So remember, we are looking here, this is meant to induce the transformation z goes to z plus epsilon z to the n plus 1. That's what Ln corresponds to. And what's the derivative of that? So the derivative of that, so this is the function zeta of z. So then we have to ask what's zeta prime of z? Well, zeta prime of z is obviously 1 plus n plus 1 times epsilon times the z to the n. That's the derivative of zeta. And then zeta prime to the half, which is what we know should appear under a conformal transformation, is then 1 plus a half into n plus 1 times z to the n times epsilon. Obviously, always plus higher order terms. And you see, this is exactly this term. This term simply reflects the fact that as I transform the field, I also have to multiply it by zeta prime of z to the power of a half. That I saw was necessary for the classical action to be conformally invariant. And as a consequence, the way the conformal transformation acts on this field is not just by z to the n plus 1 d by dz, but I get the term that comes from the conformal rescaling of the field, and to lowest order, it's just a half into n plus 1 into z to the n, and that's exactly what my calculation gave me here. So this is the sort of the first order complication that will arise when I'm dealing with fields that have a conformal factor. The action won't just be this simple derivative action, which is sort of just what the underlying coordinates do. I'll pick up a correction term, and what this is really, in general, this is the conformal scaling dimension. So if this had been z prime to the power h, this would have been h times n plus 1 z to the n. So in general, we are going to expect conformal transformation formulas of that kind, and for the free fermion, this h happens to have the form h equals to a half. Now, the one thing you may worry about is, now, is this still going to satisfy the Virasoro algebra? I mean, previously I showed to you that this term, the commutator of this term gave you the Virasoro algebra, but now I've added an additional term. So have we wrecked the conformal symmetry, or is the conformal symmetry still good? So what do we have to check? Well, we have to check that the commutator if you calculate repeated commutators, we get again the Virasoro algebra, or the bit algebra plus some central term. So let's do this calculation and convince ourselves that that is correct. So we are going to repeat this calculation I had earlier. You see, we're going to take Lm with Ln with psi of z minus the thing with the opposite order. And we know by the Jacobi identity that this should be equal to Lm, Ln times psi of z. But the left-hand side we can work out because we have worked out this formula here. So let's see what we get. Okay, when we apply it, we get a z to the n plus 1 d by dz plus a half into n plus 1 z to the n. And then we apply this, and then we apply Lm. So we apply z to the m plus 1 d by dz plus a half into m plus 1 z to the m. Right, this is what this commutator gives us, applied to psi, and then we have to subtract from it the term where we do it in the opposite order. So it's z to the m plus 1 d by dz plus a half into m plus 1 z to the m, z to the n plus 1 d by dz plus a half n plus 1 z to the n, and all of this will be applied to psi z. That's according to this formula what the left-hand side will give for us, right? That's just working it out, just like we did for the free boson. Okay, so this is again a commutator. So what are the terms that will contribute? Well, the terms that will contribute is if the z hits here, and if the z hits here. And likewise here, I'm going to get the term if the z hits here, and I'm going to get the term if the z hits here. These are the terms. I mean, when you calculate the commutators, you know, everything else will just obviously commute. These are the pieces that will not commute. So what are the terms I'm going to get? So from this, I'm going to get as m plus 1 z to the m plus n plus 1 d by dz. This is what this term is. Then this term I have to subtract minus n plus 1 z to the m plus n plus 1 d by dz. So this is this term and this term. And what does the other term give me? Well, this gives me a plus. From here, I get a half into m plus 1 times m from here, and then I get a z to the m plus n. Right? It used to be z to the m plus n plus 1, but the derivative had reduced this by 1, so this is a z to the m plus n. And from the other guy, I'm going to get minus a half into n plus 1 times z to the m plus n. Right? So this is what I'm going to get, all applied to psi. Still following? Falling asleep? Hungry? Okay, so the first two terms is obviously what we are used to. So the first one gives me m minus n, z to the m plus n plus 1 d by dz. Okay, that's what we expected. That looks good. And what's the second term? Well, let's stare at the second term. The second term is plus a half into, now we have m squared minus n squared plus m minus n times z to the m plus n. And now you recognize this is precisely m minus n into m plus n plus 1. Right? Because m minus n times m plus n is m squared minus n squared, and the plus 1 gives you the m minus n. And therefore, you see, when you factor out the factor of m minus n, this gives you m minus n into z to the m plus n plus 1 d by dz, plus a half into m plus n plus 1 z to the m plus n, acting on psi left. And that is exactly m minus n times Lm plus n, right? Because this looks exactly like this, provided that I replace n by m plus n. So this is exactly m minus n, the commutator of Lm plus n with psi. So therefore, we haven't wrecked the Virasoro symmetry, so this conformal factor hasn't destroyed our symmetry. We still get the Virasoro algebra, obviously up to a central term. There can still be a central term, just like there was for the bosons. That is it. And again, so we know what this tells us is that the commutator of this is true up to something that commutes with all the psi's. Something that commutes with all the psi's must commute with all the b's. Something that commutes with all the b's obviously commutes with the l's, because the l's are bilinear in the term, so bilinear in the b's. So again, that tells me I get the Virasoro algebra, I get the Witt algebra up to a central term. Again, I can work out what's the central term. So what do I work out in this case? I just work out, I do the easy peasy calculation rather than the strong men don't need group theory calculation. So what's the easy peasy calculation? Well, let's remember what this B. So remember, Ln is equal to the sum over R times Bn minus RBR. So let's evaluate. So we have a Fock space. On the Fock space, the positive BRs are going to be 0. Remember, the R's are half integer valued, so there is no zero mode to worry about. It's only either positive or negative, so the positive ones kill, and the negative ones don't kill, but they're fermions, so you can have each fermion only once. So what's L minus 1 on the ground state? Well, L minus 1 on the ground state, you would need 2 B minus a half fermions, but that you can't have because they anti-commute to 0. So obviously that term is 0. So the first term that survives, and then again, so from that follows that with these conventions, C minus 1 is 0 because L1 obviously also annihilates. This is obviously also true for L plus 1. So we know that the C1 minus 1 term is 0. The L0 term again is 0. So you can also see that in this convention, this central term is 0. So again, we know we are in the standard canonical form. So then the only thing we have to calculate again is L minus 2, and then evaluate L2 on it. So what is L minus 2? Well, there are two terms that contribute. I can either choose R to be equals to minus a half. So I have minus a half times B minus 3 halves times B minus a half minus 3 halves B minus a half B minus 3 halves. These are the only ways in which I can write down two modes that add up to minus 2 and that don't involve a positive mode. I mean, there must be half integer modes, negative, that add up to minus 2. There's only minus 3 half and minus 1 half. So if R is equal to minus a half, I get this term. If R is equal to minus 3 half, I get this term. Now, obviously, these two terms are not distinct because I can invert this. So when I invert this, this term is obviously equal to plus 3 halves times B minus 3 half times B minus 1 half. And therefore, with the minus a half, this is actually equal to B minus 3 halves, B minus 1 half on the vacuum. That's what L minus 2 on the vacuum is when I express it in terms of these free fermions. Okay, so now I can work out as before. Now I have to work out what's L2 on this. L2 on L minus 2. Well, it's L2 on this guy, so it's L2 on B minus 3 half, B minus 1 half, plus B minus 3 half, L2 on B minus 1 half on the vacuum. Now we have to remember what the commutators of the L's with the B's are. The commutators of the L's with the B's have this funny correction term, right? So the commutator of Lm with BR is minus R minus N over 2 times Bn plus R. That's the commutator I derived before. So now, obviously, the mode number is, so then this will be proportional to B 3 halves. So this is obviously 0 because the positive B modes kill the vacuum. This will be proportional to B plus 1 half. That has a chance to survive. So what's the coefficient here? So R is equal to minus 3 halves. So I get 3 halves minus N is equal to 2 minus 1 times, so if I calculate L2 on B minus 3 half, I get this, which is a half into B a half. So therefore, what I find is that L2 on L minus 2 on the vacuum is equal to have I done something wrong? Yeah, I've forgotten a factor of a half here. So there's a factor of a half outside. So there's a factor of a half here. So there's a factor of a half here. So I get a half into, and then I get another half into B a half, B minus a half on the vacuum. And that I can again use the usual anticommutator. So what you find is that this is equal to a quarter times the vacuum. And remember, this quarter is equal to C over 2. This is, on the other hand, this is equal to 2L0, sorry, to 4L0 plus C over 2. If I replace it by the commutator, so you learn that C over 2 is equal to a quarter, i.e. the central charge of a real fermion is equal to a half. A fermion has half the central charge to a boson. And again, there's no ambiguity here. This is not because I feel like saying that a fermion has central charge a half. It comes out of the consistency of turning this into a conformal field theory. I virtually had no choice in anything I did. So you see that a fermion has a central charge a half, a free boson has central charge 1, and now you may think that all conformal field theories have central charges that are either integers or half integers. This is like the physicist who steps out of the house and sees 2 blue cars driving past. He will come to the conclusion that all cars are blue. Now, this is a miscalculation at that stage. Not all conformal field theories have half intercentral charge, but those that have half intercentral charge or intercentral charge have a reasonable chance to be a free field theory, but there are many that are not free field theories, and the theories that are not free field theories will generically have central charges that are not equal to a half integer. And we will see examples of that later on. So what I'll do next time, i.e. tomorrow, is, so I'll treat one more example, because there's actually an interesting construction you can do if you consider n fermions. Now you would say, okay, come on, n fermions, what's the big deal? So, okay, you'll get central charge n over 2, everything will just be coupled, but if you can construct an affine Kac-Moody algebra out of n free fermions in a very canonical way, and that I'll explain to you, and that will be another important family of conformal field theories which we can introduce more or less for free in this manner. So you'll see exactly how this affine Kac-Moody algebra comes about. That will be the other sort of building block for our later conformal field theories. Then I'll explain to you how to calculate correlation functions, and then we have acquired enough experience for what to expect to formulate the theory a little bit more abstractly and understand a little bit more abstractly how the structure of a conformal field theory can be described, and that's what I start explaining tomorrow. So I'll see you tomorrow morning.